We will continue learning about the second law of thermodynamics that focuses on refrigerators and heat pumps. We all know from the experience that heat is transferred in the direction of decreasing temperature from high temperature to low temperature mediums. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. It requires special devices called refrigerators. Refrigerators, like heat engines, are cyclic devices. The working fluid used in the refrigeration cycle is called a refrigerant. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle, which involves four main components: a compressor, condenser and expansion valve, and an evaporator, as shown in the given figure. The refrigerant enters the compressor as a vapor and is compressed to the condenser pressure. It leaves the compressor at a relatively high temperature and cools down and condenses as it flows through the coils of the condenser by rejecting heat to the surrounding medium. It then enters a capillary tube where its pressure and temperature drop drastically due to the throttling effect. The low temperature refrigerant then enters the evaporator where it evaporates by absorbing heat from the refrigerated space. The cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. A schematic of the refrigerator is presented in the following figure. Here, QL is the magnitude of the heat removed from the refrigerated space at temperature TL. QH is the magnitude of the heat rejected to the warm environment at temperature TH. And W net in is the net work input to the refrigerator. As discussed before, QL and QH represent magnitudes and thus are positive quantities. The efficiency of a refrigerator is expressed in terms of the coefficient of performance. Usually we denote it as COP subscript R. Since a refrigerator's objective is to remove heat, QL, from the refrigerated space, a work input of W net is required to accomplish this. Therefore, the COP of a refrigerator can be expressed in the following form. The conservation of energy principle for a cyclic device can relate work and heat as follows. Therefore, the COP relation becomes the following expression. The value of COPR can be greater than unit T. That is, the amount of heat removed from the refrigerated space can be greater than the amount of work input. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump. Refrigerators and heat pumps operate on the same cycle but differ in their objectives. A refrigerator's objective is to maintain the refrigerated space at a low temperature by removing heat from it. However, the objective of a heat pump is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a low temperature source such as well water and supplying this heat to the high temperature medium such as a house, as shown in the given figure. A heat pump's performance is also expressed in terms of the coefficient of performance. We usually denote it as COP subscript HP, defined as the given expression, which can also be expressed as presented. The COP for a heat pump and COP for a refrigerator can be linked through the following formulation. This relation implies that the coefficient of performance of a heat pump is always greater than unity since COP refrigerator is a positive quantity. Let us discuss example 6.3 about heat rejection by a refrigerator. In this example, the power consumption of a refrigerator is given. Therefore, the COP and the rate of heat rejection are to be determined. We must specify our assumption to simplify the analysis. The refrigerator's coefficient of performance can be determined by dividing the heat removed from the refrigerated space with the power input of the compressor, as shown. Based on the answer obtained, 3 kilojoules of heat is removed from the refrigerated space for each kilojoule of work supplied. As demonstrated, the rate at which heat is rejected to the room is determined from the conservation of energy relation for cyclic devices.